Hi everyone. So in the last lecture we talked about and introduced distributions, and in this lecture we're going to talk about measures of central tendency and dispersion that are associated with distribution. So to start out, theoretical distributions like the Gaussian or others are sometimes used as models for the population. Frequency distributions or histograms are those that we'll compute from observed data. And in this lecture we're going to talk about the important quantities that summarize relevant aspects of a distribution. And like I said, our focus will be on measures of central tendency and dispersion, although we will talk about some measures of location like percentiles and quantiles at the end. So in the previous lecture, we talked about the mean, and usually for a theoretical distribution or for a population mean, we've denoted that guy by mu. So this right here, and I've had a couple emails from students about why are you using these Greek symbols. So these Greek symbols are just typically used for population parameters. So again, I'll write Greek symbols typically denote population parameters. There's nothing magical or special about this. It just helps us keep track of what's the difference between a parameter and what's the difference between a statistic. So your theoretical population that you're interested in might have some mean mu, and that's the population parameter that you'd want to do inference on. And the most natural estimate that you'd use for the population mean would be the sample mean, and that's what I have here in this formula right here. So you'll notice I've called the sample mean, it's denoted as x bar, and the x bar is using the regular alphabet, so you have a distinction between what's a statistic, which in this case the sample mean is a statistic, versus a population parameter. Okay, so that's really all the Greek symbols are there for, so that you can separate parameters from statistics. So let's take this away. Okay, so this is the formula for the sample mean, and you'll see all it says is add up all your different observations, which we're calling xi. It's saying take those, add them up all the way from 1 to n, and then divide by your sample size. Okay, so it turns out that this quantity, this sample mean, is a good estimator of a population mean. So remember, what we want to do is we want to say something about a population in statistics, and we use a sample to do that. So the reason this guy is called a statistic is because each time if you were to take another sample or resample from the population, it would be a different value. Okay, so let's take this away. And the reason that the sample mean, x bar, is a good estimator of the population mean, mu, is because it's an unbiased estimator of mu. So what that means is, on average, it doesn't overestimate or underestimate the true population mean. On average, it is the correct value. Okay, so let's look at an example. This is a data set, and the data in this data set are the number of days until recurrence of first infection in a sample of hospital patients. So it looks like we've got 9 observations. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So our n is 9 here. And if we use the formula for the sample mean, well, this is the formula. It says take all these guys in the data set, add them up, and divide by n. And if you were to do that and do a little bit of rounding, you should get this value, 14.9. So this sample mean is an unbiased estimate of the population mean. So what you should understand is, of course, this number is not exactly equal to the population mean. So this 14.9 wouldn't be the true mu, but it's an unbiased estimate of mu. Okay, so if we were to repeat this process over and over and over, this process of taking a sample from the population of hospital patients and looking at the number of days until the recurrence of first infection, and so if we could do that over and over and over, then on average the sample means from each of those would be equal to the true population mean. Okay, so later on we're going to quantify just how far off is this, can we expect this thing to be from the true population mean mu. So what's the level of uncertainty in this? How far is it off from mu? Okay, that's what statistics will help us do. So let's take this away. So that's a example of how to calculate the mean. It's a really simple computation. So another measure of central tendency is the so-called median, and the median is the middle value of the data. So 50% of the data is below the median and 50% of the data is above the median. So if you wanted to compute it, you just need to order the data in increasing order, and if there's an odd number of data points, then you'd take the middle one. So in our current running example from the previous slide of the hospital patients data, this would be the ordered data set starting from 1 all the way up to 100 days. And if we count 1, 2, 3, 4, 1, 2, 3, 4, this guy right here, this observation of 4 days until time of first infection is the median. It falls in the middle of the data once it's arranged in order. Okay. So again, the median is a relatively simple thing to compute too. So you may ask, well, what if you have an even number of observations? How would you compute the median? Then there's really not a middle observation, but there are kind of two middle observations. So let's look at the data set of the hospital patients, but let's take off one of the observations. So let's take off this guy right here, this 100. Okay, so that's this data set. It's the exact same data set, except we've taken the 100 out. So if you want to compute the median in a data set like this, well, you have an even number of data points. So n would be 8 for this data set, and what you would need to do is just average the middle two. So these two observations would be the middle two. Why is that? Because you've got 1, 2, 3 and 1, 2, 3 on each side of that. So hence the median for this data set would be the average of those two. So 3 plus 4 divided by 2, or 3.5. Okay, this brings up kind of an interesting observation. The median for this data set is 3.5, and the median for the data set with 100 left in it is 4. So these two medians are relatively close to each other. Okay, so 3.5 is not too much different than 4. Well, what about the mean of this new data set? So the mean of this data set, where we've deleted 100, if you actually carry that out, that computation, you'd get this. But the mean in the data set that had 100 in it was this. So we get a somewhat large discrepancy between these two sample means, and we only took one data point out. So this is an illustration of how the mean can be influenced by values that are more extreme than the other data points in your data set. And these are the so-called outliers. So 100, the value 100 is kind of different than the rest of the values here. So there are formal ways and formal metrics in order to tell whether or not a data point is an outlier, which we may discuss later. But an outlier just means, generally speaking, a data point that's more extreme than the others. So this example illustrates that the mean is influenced by outliers, but that the median is more robust. So the median doesn't change much in the presence of outliers. So it's actually less sensitive to outliers in the data. The mode is another important measure of central tendency, and for a frequency or empirical distribution, so remember, frequency or empirical distributions are those computed from the observed data. Then the mode is the most frequently occurring observation. Okay, so it'll usually correspond to a peak or peaks in the histogram or frequency distribution of the plotted data. Okay, so for a theoretical distribution, like the normal distribution, again, it's where the peak occurs, but usually you're looking at, say, a density function. So this would be kind of a graph of a theoretical distribution that has two modes. So here and here. So for a normal distribution, there's only one mode, and the mean, the median, and the mode are in fact equal to each other. Okay, so for certain skewed distributions, so right, for instance, here we have a positively skewed distribution. You'll see that the mode, so the peak, the point that corresponds to the peak on the graph, is less than the median, and that's less than the mean. For a skew in this direction, so for a negatively skewed theoretical distribution, you have the opposite happening. So here's the mode; it's corresponding to the peak of this theoretical distribution, and the median is to the left of that, and the mean is even to the left of that. So let's take this away. So essentially, there may be multiple modes in a histogram, or also in a theoretical distribution, like it's pictured here. So what about measures of dispersion? We've talked about measures of central tendency, and actually measures of central tendency do in fact give you some idea of the location of the distribution as well, but they're even more specific than that. So they not only give you an idea of the location, but these mean, median, and mode also give you an idea of the center of the distribution. So what about measures of dispersion? So the most common measures of dispersion are the variance and standard deviation, and what I have here in the first bullet is the formula for the sample the sample variance, and we've denoted this guy by s squared, and it's a regular alphabet because it's not a population parameter. It is a statistic. It is a value computed from data. So for instance, this statistic or this estimate would be a good estimator of the population variance, which we typically denote as sigma squared. And you'll recall that from the last lecture. So we looked at the theoretical normal distribution, and we talked about the quantities sigma, which were the standard deviation, and then the square of that, which is the variance. Okay, so again, keep in mind these Greek symbols, there's nothing magical about them. It's just how we denote population parameters and how we distinguish or keep that notation separate from statistics or things that you estimate from the data. Okay, so let's take this away. So what is the formula? What's going on in the formula? Well, basically, what you see in the numerator, or you see the sum of all the squared deviations of each observation from the sample mean. So what we have in the numerator is the distance or difference between each observation and the sample mean. We square that quantity and we add all those up. And then the quantity that we get from doing that is divided by n minus 1. Okay, and for the for the sample standard deviation, it's simply the square root of that quantity. Okay, so the variance and standard deviation, these are measures of dispersion around the mean. And you'll note, and you may ask, why are we dividing by n minus 1 here in this formula and not n? And the reason that we're dividing by n minus 1 is because if we divide by n minus 1, then the sample variance, it turns out, will be an unbiased estimate of the true population variance, sigma squared. And sometimes n minus 1 is referred to as the degrees of freedom. And intuitively, that comes from the fact that you've used up 1 degree of freedom when you estimate the mean here in the formula. Okay. So let's take this away. So let's look at an example. And this is an example from the book, and it's the serum levels of high-density lipoprotein cholesterol in N equals 26 participants. So this will, you'll see abbreviated sometimes as HDL. Okay, so this is the data set of the 26 measures in the participants, and I want to point out that your book has a slight error in the formula for the sample variance. Here, what I've written here in this formula is an equivalent and convenient computational formula for this guy right here. And the reason that we have a different formula is because mathematically they're equivalent, but it just turns out that this formula requires less amount of computational work. Okay, but the book has a slight error here. It's missing the square term. Okay, so I just want you to keep that in mind. So for the HDL data, if you were to actually carry out this formula, you do these computations for that data, you would find out that your sample variance, after some rounding of course, is 171.94, and if you wanted to compute the sample standard deviation, then you would essentially just take the square root of that number and you would get 13.11. So let's look. So we have these things that we've written for the last, some notes for the last set of lectures. So let's look at what would happen. How can we get an idea of what the variance or standard deviation, what kind of changes would they produce in the corresponding distribution function? So let's just, for simplicity, assume that we have a standard normal, not a standard normal, but let's just assume that we have a normal distribution that's, say, centered at 0. So we'll let it have mu equals 0, and let's say sigma 1. Okay, so if we were to plot this normal distribution with mean 0 and standard deviation 1, it would probably look something like this. And I'm not being 100% exact here, but I just want to give you an idea. Okay, so for the normal distribution, it turns out that this point, the mean, mu, is also equal to the median. So what that means is that 50% of the area underneath the curve is to the left of mu, and 50%, all right, 50%, and 50% of the area under the curve is also to the right. of mu, so 50%. So this guy is also the median. So mu is equal to the median, and the peak on this curve occurs also at mu. So mu is also equal to the mode. Okay, but now what would happen if I increase my variance? So let's just say instead of sigma equals 1, let's say I look at a normal distribution with sigma equals 10. I'm going to keep the same mean, so I'm going to keep this thing centered at 0. But what would happen if we increase our standard deviation in this way? So you would get a much flatter curve. Okay, so this is kind of the overall, this is an overall description of what would happen if you increase your standard deviation. Well, what if we did what if we decreased our? So before we do that, why do you think that that the graph would look more like a horizontal line, that it would be stretched in this way if I increase my standard deviation to 10 versus 1? Well, you have more dispersion around this mean point, so your distribution is more spread out. Okay, so hence it becomes flatter. Now, if we were to decrease sigma, let's say we want to look at a normal distribution with, instead of sigma equals 1, let's say sigma equals half. So what would that do to the corresponding distribution? Well, it would just, as you can probably intuitively guess, it would make it more peaked. So you would have something that looks more along the lines of this. So we're going to still keep our center at 0. But now what you see is that you have a distribution that's less dispersed around the mean. So there's less variation or less dispersion in this distribution. Similarly, so these are for theoretical distributions. So this is these are graphs supposedly supposed to represent the theoretical normal distribution. So this is supposed to be a normal with mean 0 and sigma equal to 1/2. Similarly, if you had a data set and you looked at the empirical distribution, if you had a data set that had sample variance, say 1/2 versus sample variance of 10, then you would see this similar type of behavior in the empirical distribution. One would look more stretched, and one would look more peaked. Okay, so that hopefully gives you some intuition of what this variance or standard deviation is kind of capturing in the distribution. Okay, there are some more measures of dispersion. So for instance, the range is a common one. It's just the maximum value minus the minimum value. It's not really used too much. It may be used in a descriptive type of characterization, but it typically not used in any kind of inferential situation. Another set of summaries that are useful, and they give you an idea of also location, which the mean and the median and the mode do give you an idea of location as well. They kind of tell you where on the x-axis your distribution sits. But these are some more. So quantiles and percentiles give you an idea of where the graph or the distribution sits, and their differences. So the difference between certain quantiles gives you an idea of dispersion as well. Okay, and we're going to talk about that in a second. So what's the definition of these percentiles? So the pth percentile is the value such that p% of the data is less than this value, and we're going to look at an example of how do we actually compute some of these things. There are special denotations for the 25th percentile, the 50th percentile, the 75th percentile. So the 25th percentile is called Q1, and sometimes that's called the first quartile. And the 75th percentile is denoted Q3, and that stands for the third quartile. Okay, so for the 25th percentile, or Q1, 25% of the data has value less than that value. For the 75th percentile, or Q3, 75% of the data would have a value less than that data point. Okay, and these quartiles are used to form box plots, and they lead to another measure or quantity that gives you an idea about the dispersion in the data, and that's this IQR. So interquartile range is what that stands for, interquartile range. Okay, and the definition of that is just Q3 minus Q1. So it's just the 75th percentile minus the 25th percentile. And what you'll see is this data, so let's go back. So this cholesterol, serum levels of high density lipoprotein cholesterol data is what you see here in this system of graphs. So the very first one that you see is the so-called stem and leaf plot. This is one way to help you visualize data and get an idea of whether there's skew in the data, whether there could be potential outliers. So it's more of a visual thing. And how is it made? How do you make it? So you have this first important column, the stem, and it's basically just the leading digit, the leading place in your data that you want to start out with. So in this situation, for this data, it's the 10th place. Okay, so when you identify that and you figure out which place makes the most sense for graphical purposes, then you write each observation in order after each of these digits in the stem. So for instance, let's just focus here. So we decided, if we had decided that the 10th place was the most natural place for our stem to be, then how do we write the leaves? Well, let's go back and look at our data set and see how many 3s we have. Well, we only have one number that's in the 30s, and the value after the number 3 is a 1. So that's where this number comes from. So 1, and we have one of those data points in the 30s. Okay, let's move up to the next one. So that would be in the 4th place. So here, and if we go back and look at how many numbers we have that are in the 40s, we've got these, and what you'll see for the leaves in the stem and leaf plot will be these digits in order. Okay, so let's go back to, and that's precisely what you see here. You see those trailing leaves, and there were 8 numbers that occurred in the 40s, and so on and so forth. You can see now the general pattern of how you fill in a stem and leaf plot. Okay, and you would do the same for the 5th place, the 6th place, the 7th place, the 8th, and the 9th. So if you look at this data, you can get an idea. If you look at the stem and leaf plot of this data, you can get some kind of idea, if you were to draw a graph, some type of density or distribution function over these numbers of how that would look. Okay, again, these are primarily for illustration purposes, for graphical purposes, for data display purposes. You wouldn't necessarily do any statistical inference or hypothesis testing based on these graphs. They would just give you an idea of what the data looks like. But it's always good to plot your data first before you do any analysis. Okay, what you have in this spot is the so-called box plot, and the box plot's made up of a bunch of boxes, a few boxes, and these so-called whiskers. So where do the boxes come from? So this first box would be Q1. So this would be the data point denoting the 25th percentile, or the first quartile. Those two terms mean the exact same thing. Okay. What you have in the center here is the median, or the 50th percentile, or you might call it Q2. And what you have here in the upper box would be the 75th percentile, or Q3, the third quartile. Okay? Now, so those are your boxes, and that's how your boxes are formed. And what you have here are the so-called whiskers. And these whiskers go out to 1.5, so they go out to 1.5 times the IQR in both directions. So what this lower whisker would be denoting is a line from Q1 all the way down to 1.5 times IQR. Okay, so let's take this away. Similarly, for this upper whisker, what you have is a whisker that goes out to 1.5 times the IQR above Q3. So Q3, Q1, and median, or Q2. Okay, and then finally, what you'll see sometimes in a box plot are these so-called outliers. So those are the observations that are outside of the whiskers. So they're outside of 1.5 IQR, above or below Q1 and Q3. Okay. And finally, what you see down here are the actual numbers for each of those quantities, and more actually. So Q1 was computed as 48 from the data. The median is 57.5. Q3, or the 75th percentile, turned out to be 64, so that would be this observation. And you have output about the range, the IQR, which is Q3 minus Q1, and the mode. Okay, so let's take this away. So what are some conclusions? So in this lecture, we've introduced some important quantities that summarize distributions. So distributions are typically talked about in terms of important summaries of them. So for instance, their mean, their median, their mode, something about the dispersion of the distribution, and the ones that we talked about fell into the general categories of measures of location and measures of dispersion. And it just so happens that measures of central tendency are a special subset of measures of location. In the next set of lectures, we will start Chapter 10, and in Chapter 10 we're going to discuss important concepts in statistical inference and hypothesis testing. Thank you.